we look forward to listening. I think the sort of logistics is, I don't know if you prefer to be interrupted with questions or we save them at the end, or.
Given the size of the audience, probably at the end would be better.
Okay.
And I'll say, I have nothing scheduled after this, so I can, I'll talk about 40 minutes maybe.
All right, let's do
Okay.
that at the end, unless there is a quick burning question. So
Okay.
please go ahead, it's all yours. Thank you.
Yeah, I want to thank everybody for attending today. When Maria called and asked me if I'd do this, I was very excited because I've sat on several MIT advisory boards. I'm on the storage advisory board right now, and plus being CEO of an RTO was a lot like being the groundskeeper at a graveyard. You're over a lot of people, but you're not sure anybody's listening to you. So having this audience of technical experts is just my pleasure. Let me get started here. I titled the presentation today, Blackouts. Blackouts, is the screen up?
Yes.
Yeah. Blackouts, past, present, and future. What I want to do is talk about the importance of what we in the electric industry do each and every day, and kind of give a brief summary of the blackouts that have occurred since the great 1965 blackout, and then talk about what the future concerns are likely to be as we go forth. And I have a slide at the end that says the future ain't what it used to be, and I can assure you that's the case. When the National Academy of Engineering was asked what are the most important engineering achievements of the last century, it's not a surprise to this group that the grid and electrification was number one. You can't think of anything that has improved our productivity more, improved our standard of living more, as those people in Texas can tell you that recently had the power outage in February. But more importantly, 6 of the remaining 9 are powered by electricity. So important things like refrigeration for our food, no botulism, water supply that's clean that we can have no cholera. And we're headed to a world where automobiles are going to be powered by electricity more and more. And my biggest fear in terms of the planning is that we don't have enough load growth in our forecast to handle the electrification of everything, including transportation. But microgrids are very much in the move. Does anyone know how long it takes to build a microgrid? I actually know the answer to this. It takes about 5 days. This is New York City, Wall Street. On your left, the cabling looks a little like a third world country, but to get the markets back up and running after Superstorm Sandy, we had to do some very quick and exciting things in terms of 2 megawatt diesel generators. And this was a 2-week event, kind of. Sandy was not a long duration outage, but I want to emphasize microgrids and the importance of telecommunications and communications. This guy looks like a lean, mean biking machine here. He's found that he can charge iPhones using a DC generator on his bicycle. And by the way, he is about 20% efficient. The bicycle is about 95%. So I figure that he can charge 4 iPhone 13s with 1 slice of pizza that he can buy for 99 cents. So he's found a niche market. However, if he was running a 3,000 square foot home, you would need about 30 to 40 of them, and the pizza boxes in the front yard would not be acceptable to your neighbors. Power engineering is not rocket science. It is much more important than that. At the end of the day, the loss of life, the shutting down of the economy that occurs when there is a blackout is not acceptable. So my focus today will be on how do we keep the power on and avoid blackouts as we look at both history and the future. I had an interesting call. I was head of power supply in the mid-70s. I had an interesting call from Marshall Space Flight Center in Huntsville, Alabama, and they wanted a guarantee of 7 years without a power outage because the father Voyager that launched in 1977 got out in space, the less likelihood that they would be able to find the radio signal and tune back in on it. So if they ever lost the radio signal, they were afraid they wouldn't be able to. And I was thinking Marshall Space Flight Center, Huntsville, Alabama, Tornado Alley. There's just no way you can guarantee a 5-year, 7-year period without a power outage. But I said, we can't do that, but we can come down with the folks that have designed our control systems and backup power supplies, and we can show you how to do a microgrid that will assure that you have power for those radios. And by the way, 44 years later, 15 billion miles away, we're still getting interstellar data. And surprisingly enough, seeing radio frequencies out in the interstellar space. Unfortunately, this will run out of plutonium on the battery around 25 or 2027, somewhere in that time period. But you can do microgrids and you can back up the power supply is my line here. I'm going to run through very quickly the blackouts of history. I'm not including the Katrinas and the Andrew 1992 blackout, but the ones where us engineers were involved. So if you think about the big blackouts, the Northeast blackout of 1965 kind of changed everything. 30 million people in the dark. Relay engineers had miscalculated a relay on the 230 system, had set the relay, and even more importantly, they had not told the reliability coordinator that they had changed the relay settings. And so at Niagara hydro plant, near Niagara hydro plant, misoperation of relays caused that cascading failure. Some very good things came out of this, though. We created EPRI, the Electric Power Research Institute. 2 years later, NERC was formed. We built more 500 kV lines right after this event to intertie and make the backbone of the nation than we've ever built, and before or since that event. So some good things came out. Some bad things happened. This is a full moon over New York. This is can you imagine being on a surgery operating table in New York? And unfortunately, even during Superstorm Sandy and this event, a major portion of the hospital generators failed after they had run for several days, especially during Sandy. Second outage was an operator error. Muddy Run pump storage plant had just been completed. We hadn't built all the transmission we needed to easily run the pumps and the generators. And when they were going from pump mode to generate mode, they were supposed to split the bus so the generators would be distributed out through the system. The operator failed to split the bus. We had an overload that occurred. Lines started tripping. We lost 2 major generating stations connected at 500 kV. And more seriously, the frequency dropped to 53 hertz before the cascade was over and stayed there for a while. So you worry about damaging generators and this was before our load shedding under frequency relaying was put in place. That was actually driven by this 1965 blackout. This one was not as big, but it was not pretty either. We had 2 almost simultaneous 345 kV lines struck by lightning, and we still have what they call emergency storm operations, so that we increase local generation in New York. But the thing that wasn't pretty here was society was in a kind of a bad position. This was after the oil embargo in 1977. There was a coal strike going on. We had high inflation. My house mortgage was 18% at that time. I remember quite well. And so society didn't turn out pretty. We had looting, store windows broken, fire set during this outage. It was probably the worst all of the outage we had. July 2nd, 1996, a tree on the Idaho border was sagged into with the 345 line. There was a sympathetic trip of adjacent line. Sympathetic trip meaning a misoperation. The relay saw through the fault and tripped an adjacent line, causing an area about 14 states to go in the dark. This was unfortunately this was of national interest, and it took about 35 seconds for the system to divide into 5 islands. And by the way, my cousin actually wrote a report to President Clinton saying, hey, we're working on this, we'll tell you. And the next day, same tree, same overload, it happened again. And unfortunately, the misoperation of the relay happened again. But the operator had 30 seconds and he knew it was a misoperation and restored the line, and the blackout did not occur. But for the ink was dry on that paper that went to, on the letter that went to the president, another event occurred. 100-degree day, it was quite hot. Several lines overloaded and sagged into trees, and we had a similar area covered by an event. So I remember well the emphasis that, hey, the markets are not causing these problems. This was temperature and overload conditions. This one I kind of slept through. I don't know why it lays loud on my constitution. I've studied through time or currently most of the outages, but a 345 line was hit by lightning, and the phase angle differences, there was large transfers going between Canada and the US. The phase angle differences were so large that they could not close it. They were synchronous, but they couldn't close the breaker because of the phase angle differences that there were on the system. Another line got hit, 345 line, by lightning, and the system cascaded. Probably not fair that I list this, but it's too much fun not to. This was the market failures of California, the energy crisis of 2000, 2001. And to show that electricity is important and it's political real fast. Gray Davis was governor when those market failures and the rotating outages occur. There was a whole lot about stick it to grandma and the markets that were trying to happen. And this was a poor market design. But there was a bumper sticker, and I tried to find it on my computer. I have a picture of it somewhere. But Gray Davis as governor, there was a bumper sticker that came out and it said Blackout 2001, Gray out 2002. And sure enough, Gray lost the gubernatorial election in 2002. Texas, May 5th, 2003. Started at a nuclear plant. We had an under frequency excursion, not a total blackout, but lost 4,000 to 5,000 megawatts due to the under frequency excursion that occurred. The big one, I was on the blackout investigation team for this at NERC, and pretty straightforward. 2 trees and 2 computer failures was the root cause of this outage. And the computer failures were fairly serious. The SCADA coming into Akron was frozen, and data was coming in, but it wasn't correct data. And in Indianapolis, the state estimator had inadvertently been turned off, so they were flying blind. This took a long time, more than an hour to propagate, and we had a lot of swings within islands. Fermi nuclear plant dropped to 49 hertz and was still trying to run when the reactor feed pumps tripped. So there was some damage to equipment, longer term, not necessarily instantaneous damage. to the equipment that occurred. But coming out of this, we had a bumper sticker that came out that said tool training and trees. And any operating executive that'll let a tree get into a high voltage or extra high voltage line made the news. So I had, interestingly enough, I restored a lot of the right-of-way budget when I was at TVA after that, because I sure didn't want to have credit for a tree causing a widespread outage. Commute was pretty calm and peaceful, much better than 1977. This is the Commute since the subways were shut down in New York. The bridges were converted to walking bridges to a large extent. So again, California, 2003, and rotating outages, not cascading failures. This one was most interesting in that a relay tech went into Flagami substation in Miami and took all the protection off of the relays that I'm talking about, primary and secondary protection off of the relays on the 138 system. And a fault occurred at a switch, and the fault stayed on the system 88 seconds. Now, I didn't say 88 cycles. I'm saying a long term. At the end of the day, Miami started swinging against Manitoba, and I have a video showing the two systems. The rock solid frequency right in the middle of the system, but the two ends of the system started swinging against each other. I think this was around a 4,000 megawatt outage that occurred, kind of spread across, with under frequency load shedding being party to it. September the 8th of 2011, we had two electricians were switching out a capacitor bank over on the 500 system near Palo Verde. At this time, unfortunately, California ISO did not have visibility of the system where the fault, where the problem precipitated from, excuse me. But the bottom line, the Imperial Irrigation District down at 69 overloaded. It took about 2 minutes for this to propagate, and there was time for operator intervention, but there wasn't enough data in the hands of the reliability coordinator to take operator intervention. A good news story came out of this after we put the phase angle measurement units, the PMUs here. It took us about 3 months to get to the sequence of events following the August 14th, 2003 blackout. It actually took 6 hours for Bob Cummings to come up with a sequence of events for this cascading failure that occurred. That's San Diego with a full moon, just like New York's full moon. This is all the blackouts that have been kind of, in my dictionary at least, that were engineering market kind of failures. And having served 3 terms as CERC, there's a certain amount of self-servingness is in here, but it is not easy to keep the power on all the time. Today, I want to talk about extreme events. And again, not so much the weather events and the Fukushima earthquake event, but I want to talk about where we are in the solar cycle, cybersecurity, and the EMP threat. Not many people want to talk about the EMP threat. It's unfortunate because it's very different, and I'll try to point out the differences on the slide here. In the 1980s, I was in charge of reliability as a transmission operator, and I had 2 problems. They were fairly big problems. They were lightning and squirrels. With the advent of the VCR and the home computers, a momentary outage was no longer acceptable. And so an outage that was caused by lightning, resetting the clocks on the VCRs and computers rebooting, and squirrels cause outages on the distribution system. With the metal oxide varistor lightning arresters that we put out on the line, tens of thousands of them, and the boots, insulating boots on the 13 kV stingers on the transformers, we pretty much put those two to rest, causing very few outages. However, something else was going on. 1986, the National Science Foundation set up a system, you may have heard of it, it's called the Internet, at a racing speed of 56K baud rate. We tied 5 universities to the National Center of Atmospheric Research in Colorado, and that was the start of the Internet. At that time, everybody was excited about being able to hear that buzz of the modem connecting you to the Internet. Today, the Internet looks a whole lot like this. It's a scary, scary place. 35% of all businesses in the US have been hacked. There are often cases where people are trying to get between the firewalls of the Internet and the control systems. When I was a boy and had hair on top, we would not even think about using the public switch network to bring in data for our SCADA EMS system. So we have to be very vigilant, and these are the substations we need to protect. Anybody see the problem here? It is a massive scale. Gates and guards and guns don't get it. You have to have firewalls and backup systems and ultimately manual systems as you look at trying to operate the power system in this world where systems are constantly under pressure of hackers from all around the world, including nation states. Another thing that Dan asked me about before the meeting here that is a little scary to me, and this was an NREL finding that was published earlier this year. Electromagnetic transients can propagate throughout the large geographic area given the number of inverters and asynchronous generation that we put on the system, triggering system level problems, and then on to say up to a cascading events. This is not acceptable in a design standard, and kind of my finding is we've got to find a way to assure the resiliency of these distributed energy resources. I have solar panels on my house here, and I'm for very much having distributed energy resources, but we've got to improve the design standard and then constructively challenge how the grid following inverters work on the larger power system. This moves us to blackouts present this year. Everybody saw it on the press. If you were there, you lived it. But the big freeze that hit Texas, and this was cold, but not extraordinarily cold. It's the kind of temperatures, 10 degrees Fahrenheit, that you would see here in Tennessee, and much warmer than what you would see in Chicago. But bottom line is generators came peeling off crazy. The gray on this bar shows the generator failing over 20,000 megawatts of gas-fired generators. The gray is gas on the system. And the blue, the light blue is not the difference between the generation and the nameplate capacity, but what they thought the wind was going to do and the actual wind output. It dropped to about 900 megawatts in the morning of the coldest morning of the 15th, and they had expected 3,000 megawatts. And that was a fairly serious problem in that you can buy a winter package that in essence puts heaters on the gearboxes, on the fluids to keep the fluids so the units can use. It's a little more expensive, probably $40,000 or $50,000 per wind turbine to put ice shedding, resistant heating in the blades to shed ice. But the coal-fired system didn't perform well, as you can see on the curve. nor did the nuclear. But if you had to say what's the root cause of failure, it was the wellheads freezing, and the pipelines between the wellheads and the gas drying plants. Natural gas will not solidify until like a minus 250 degrees, but you've got propane, butane, and more importantly, water. And so the freezing of the wellheads and dry air will freeze. If you don't have heaters on the pneumatic lines, even at 3,000 PSI, you'll have moisture in that air and the orifices will freeze. So from a transmission operator's perspective, and I've been there, ice storms are the scariest thing. People are in the dark, freezing in the dark. And generally speaking, ice storms hit the transmission distribution system. In the case of Texas this last year, it was heavily oriented towards the generation systems, that being the wellheads, the gas wellheads, and the windmills. Now I'm going to talk a little bit about outages, and some of which I have lived through and managed the system. On the left was my first ice storm. I had been in the control room for the first 10 years of my career, and headed up scheduling and power system control center. And I said, get me out where the real work is with the crews. This is near Knoxville, Tennessee, an ice storm 1983. I actually took that picture. James Mundy had to go up this structure, and it took us forever to get there because you had to cut your way in with the chainsaw. And I turned to James and I said, have you ever climbed a structure this bad before? He said, yep, about 20 years ago, and I didn't like it then either. So then he put on his belt and climbing gear and went up and got the overhead static, broken the ice on it so it wouldn't sag into the A phase of the double circuited line. 1994, we had 1 million customers in the dark in the TVA system, more than that in energy and other systems. This was an ice storm. We actually had 3 inches of radial ice, much more than our design criteria. And I might add, this is not electricity that you see. The lineman, and there's 2 linemen in that bucket truck. One is faster than the other. He ducked. But the 60th of a second flash photography caught the explosion of a fuse that closed into a dead short due to more trees in the line. The last structure there is from Quebec, 1998. It was awful. The ice loading was much above the design criteria for the structures, and they cascaded a lot of structures all the way up towards James Bay. And it took a long time to recover from that ice storm. So the scariest thing is people, for a transmission operator, is people freezing in the dark during or after an ice storm. So for your next polar vortex, and there will be another one, I don't know when or where, but it will be, never compromise your family safety. Have a home kit. Here I'm a little bit of a geek. I have solar panels on the roof. 10 kW is the most that TVA will let me put on the roof without financial penalties, but I have batteries in the wine cellar under my front porch that's radiologically shielded. I have an inverter that's EMP shielded, and just because I enjoy being a geek, I have a lot more than just a kit, but have a kit that thinks water, light, heat, radio, extra batteries, and because of what happened in Texas, think carbon monoxide monitor, that you're not putting your family at risk because you're using either a generator running in a closed space, or more than likely a car that people are in trying to stay warm. I'm going to move to electromagnetic storms, and what we've seen every 11 years, I get very focused on this for some reason, because, and we don't do enough about it probably in between the peak events. The solar cycle will peak between now and 2025. We had 2 storms this last summer that were orthogonal, perpendicular to the path of the Earth. Either one of those storms were comparable to the Carringer event of 1859 that melted telegraph wires and caused a lot of damage to the system long before Edison's Pearl Street Station. But the point I wanted to get to with this is we will have solar events. They will damage equipment, and it's primarily the DC source that overexcite transformers and will have generator and transformer issues following a severe electromagnetic storm due to the induced DC current. Now, EMP is quite different in that the duration is much shorter and the intensity is a microsecond that destroys primarily electronic equipment. The longer term solar storms can damage the major power equipment across the system, but you can't run the system without relays, you can't run the system without communication. So both are dang serious in terms of what could or will likely happen someday. I had the opportunity, and it was a fun group. 2 years ago, we wrote a paper on the resiliency of the power grid, what we need to do to improve the resilience. Some things like daffodils are more resilient than others. They can grow in Paris, France, or on Signal Mountain, or in your neck of the woods. But the definition of resiliency we kind of hone in on is the ability to reduce the magnitude or the duration of a destructive event. Now, I use a simpler definition. I got it from John Cameron Swayze on a Timex commercial of my youth. The ability to take a licking and keep on ticking, that you can ride through the events, have minimal disturbances, and when the event is over, restoration is very quick, and you have a learning loop that feeds back. And that's actually in the report, that every event you learn from that event, whether it's an ice storm, a hurricane, or a magnetic storm. Now I'm going to get to the future and what it used to be. I'm going to tell you what we thought in the year 2000 and kind of where we are today. In the year 2000, gas prices were through the roof. We were building gas import facilities. So we were building the ability to import natural gas. After fracking, gas became king. PJM alone ordered on 30,000 megawatts. Order is not the good word. The market condition brought on 30,000 megawatts of natural gas combined cycle plants. And this winter, gas is going to be short supply. So we kind of move around in terms of where we are. The nuclear power was poised for a renaissance. We had just come up with a standardized design, the Westinghouse AP1000, and we thought we were going to be going towards nuclear in a fairly big way, and we were going to follow the French example of where they designed and repeated the design over and over. Fukushima happened, the nuclear renaissance. I said stalled here. It's almost dead right now in terms of there's only one nuclear under construction, and cost and schedule has been a serious problem. Digital tech was driving Moore's law and processing and computing power. Today, digital tech is very focused on batteries and energy and how we do, as we were talking about, how we do low frequency control on the system. So in the distribution system in the year 2000, just keep it safe, make sure that everything is grounded and you're not having swirls and accidents. And today, the distribution system is the platform that the distributed energy resources will be built onto. It's a key enabler of where we're going. Carbon capture and storage was very much in the press. We had at least 2 projects, one in Illinois and one in Virginia, or excuse me, West Virginia, I believe it was. And today, CCS is discussed, but not seriously. And it's pretty expensive, and there's not an easy way to resolve the deep well injection of the carbon. And wind and solar. No one had wind and solar in the budget. It was too expensive, wasn't going to happen. In the year 2000, it wasn't at scale. Thanks to the tax credit and the improvement in the technology, we have built out more wind and solar than anything else. So having proved to you that we didn't know what the heck we were talking about in the year 2000, I'm going to tell you what the future, excuse me, I thought I was going to tell you what the future is. I'm going to start at 1 o'clock here and tell you what the future has to hold for us here. And this too is in the National Academy report. It's called the Boston Roulette Wheel. Are we going to have high future load growth? Are we going to stay down as we have been for the last decade as LED lighting has gotten much more efficient? And my theory is we're going to see much higher load growth than we've had in the past, primarily driven by decarbonization and electrification of everything. If you think about steel, if you think about the petrochemical industry, and obviously transportation is going to happen because it's more efficient. The electric motor is more efficient than the internal combustion engine. So my theory is we're going to see much higher load growth than anyone has in their current forecast 20 years out. Are we going to have a concentrated fuel portfolio or highly diverse, more favorable with risk being shared? Answer is going to be very concentrated. It's going to be wind and solar, batteries for low frequency control, and hopefully batteries for longer term storage as well. But batteries are going to play a big role in enabling the wind and solar to continue to grow. The price that we have for wind and solar is very attractive and will continue to get more attractive as time goes on. Are we going to have distributed self-supply, small units, DER? Or are we going to have centralized supplies with large farms and plants? The answer to that is yes. It's going to be both. I'm on the board of Blattner, advisory board of Blattner, and we've got 300 to 400 megawatt solar farms and wind farms going in. We were the largest builder of solar and wind last year, and probably we'll see the size of those utility scale solar and wind go in. Are we going to have autonomous microgrids with each and one of us controlling our own, or are you going to have centralized grid control? And the answer to that is yes. You're going to have both. You're going to have a PJM. There will be a CAISO, but when the system fails, we will have the ability to fail over. Here in my house with 10 kW, that's not enough to run the house, but of the 109 circuits that I have in the house, 10 critical circuits, important things like refrigeration, fan for one of the gas units is not a heat pump, fan for that gas unit, so I got heat, and microwave oven so I can cook a pot pie. So basically speaking, I have hardened the Boston family home so it can run for an extended power outage. Now, I am a geek. Not everybody's going to do that. But at the same time, people need to be thinking about what happens if there is a long outage. And Hurricane Andrew, it took 4 weeks to survive and recover from Hurricane Andrew. Now, escape to where the puck is going to be. Wayne Gretzky, the greatest hockey player, well, among the greatest, I'll say, some of you may disagree, said a good hockey player skates to the puck. A great one skates to where the puck is going to be. The puck is in the center of the screen, bottom part, thyristor. The power electronics we're putting on the network is going to change the network significantly. I have written papers and believe that HVDC is a big part of the answer to the integration of our wind and solar. But more importantly, power electronics is going to play in the microgrids and grids that can isolate on critical loads, like our military bases, like our hospitals, et cetera. And they will, in essence, when the grid goes down with local generation, critical loads can be served by those microgrids, including batteries for load frequency control to balance the system. And you kind of need batteries on both sides of the microgrid and the grid. But going forward, we're going to see a major change, and that's the reason the importance of load following inverters has got to be resolved here very quickly. One of the neatest things that I've seen lately is ADC Energy has come up with ability in a 3-wire system like I have here in my house to superimpose DC and AC on the same 3-wire system. Think of this, if I wanted to plug in my computer over here with an inverter, I would plug it into a 3-prong outlet. If I wanted to plug it in directly, I could plug it in with the 2 wires going from the neutral to the ground. So I would have both AC and DC distributed throughout the system. Every AC to DC conversion that you do, or DC to AC conversion you do, costs about 7 to 10% losses. So if you could have DC buses with microgrids, it would firm up and make those critical lifeline systems that we have, that we depend on. And electricity, you can ask the people of Texas, electricity is a little like water and oxygen. It's kind of required for the life as we know it here on Earth today. So this is almost something that I think will change the way we design our system. 70% of the buildings that have to meet the zero carbon by the year 2050 have already been built, have already been wired, and therefore being able to not have to rewire everything to take advantage of the DC voltage that we have with solar panels and the distributed energy is a big deal. I want to close exactly where I started. Electricity, carrier of light and power, provider of time and space, bearer of human speech over land and sea, greatest servant of man. This was carved in stone at Union Station in 1908. It's just as true today as it was. If you come out of the Capitol to Union Station, the train station behind the Capitol, look up to your upper left, and you'll see this carved in stone. My point being, electricity, nothing has improved our standard of living more, nothing has improved our economics, our GDP, our productivity more than electrification. So with that, I will try to take any questions that we have. And if I can't answer them, I'm going to get Marie to answer.
Thank you very much, Terry. I wish this was all in 3D, but you know, we are enjoying what you told us. It's absolutely amazing journey that you gave us. And while people are getting ready for questions, I want to ask a sort of university focused question. What has happened, and you know, some of us are getting really older. I think universities are usually like 10, 20 years ahead of the time of what could be and should be done for, in particular, for electric power industry. And if you remember late Professor Fred Schweppe, at MIT. He was my role model. He brought me to MIT to work on both markets and technical stuff. And, those were tough times for university people, and they still are. So can you comment a little bit on how to bridge that gap? How do you do innovation in a way where, where you really want to follow the puck, and skate there? And what are the risks? What would be your advice to a lot of young people here who are excited about, helping? I see students, they are now defense students. They're not doing just because, they want to do engineering. They want to help with the problems that you are talking about. But on the other hand, the path is not very well defined. How do you innovate? And can you comment a little bit on all of that?
Yeah. First of all, in the 1990s, electric power became very unsexy.
Yeah.
But I mean, it was, we were cutting costs on every corner. We weren't hiring many new students coming out of college, much like the nuclear training programs that we have. And don't misunderstand me, we need the nuclear fleet to survive just for the nuclear safety of our military. The Navy has 99 small modular reactors running around with battleships, and so we're kind of in that same area. But the greening of the environment, the climate change issues, has enthusiastically got the younger population, the brightest and best, very interested in the power grid. And we need to take advantage of bringing folks into it. In China, 40% of the graduates are in engineering. Not so here, clearly. And we have to be careful, and this is not kind, but sometimes we get so heavenly minded we are no earthly good. We have to have things that can incrementally be moved into the grid. And I can give you an example. The LED light bulb is Nobel Peace Prize winning work in terms of how much energy is saved in converting that little heater 60-watt Edison bulb into a 4-watt LED bulb with the same light. But we had to design the screw-in base to match the Edison design to get it dispersed. We've got to do the same thing with DC, and that's the reason I'm really excited about what you could do with using the existing wiring system. You don't have to redefine the whole world to do there. But I think we're at a turning point because of the importance of electricity to reduce the carbon emissions, and perhaps more important, to continue to improve our standard of living and our productivity, the GDP, and therefore there's more people. But I think you're right. You need the Bob Cummings of the world, the people that have been there, done the blackout investigations to advise. ELU has done that at the current center to have people that know and understand what has happened on the grid and where the grid is going. There are people that believe that we're all going to be on autonomous microgrids and there won't be a need to be interconnected. I think those people are so heavenly minded that running your own grid is not easy. I could not survive forever with 10 kW of solar on the roof. But
thank you very much. I think it's great to hear that, young people need to hear that what they are getting is more important. So I see a question actually from Yilu Liu. Yilu, you want to ask the question yourself?
Oh, Terry, this is a wonderful presentation. I hear every word of it. I try to remember. I have an odd question. Bill Gates seemed to buy a lot of land, and one theory is he wanted to see he expect the biofuel, let's see, corn, play a big role. He wanted to, he believed the land value will definitely grow. So what's your take on this?
First of all, biofuels has a role, but it's not a big role because biofuels take so much water to make it work. So if you look at solar thermal being 50% efficient, you look at this is a passive solar room I'm in. The floor is 8,000 pounds of granite that heats up from the sun only in the winter. It's shaded totally by overhangs in the summer. That's 50% efficient. The solar panels on the roof is 25% efficient. Photosynthesis is less than 1% efficient. So to think that biofuels is going to drive and the land use, we're not running out of land, don't misunderstand me. But the land use, or more importantly, the water use that goes with biofuels will be a limiting factor. Some of the things that are happening, and I actually worked on using fertilizer off the coast of Africa, and this was 1990 under Bush 1. President Bush was working on carbon capture. If we could, in essence, increase the algae that's coming across and capture the carbon at the bottom of the ocean and increase the feedstock for fish, that's a biofuel example that I really like because it uses something other than land and salt water as opposed to fresh water. But I don't see biofuels, and I might add, people that are smarter than me and work for Exelon disagree with where I am on this. But I don't see it as a big part of the solution just because of the land use, or more importantly, the water use.
So Terry, I don't see other questions. I'm going to ask another one. I think that as a community, we need to, sort of engineering community, software, need to make a better case on how different innovations, engineering innovations, impacting decarbonization. For example, my favorite thing is maybe, like if you look now at reserves, let's say the ISOs have, it's not 100% guaranteed that they are deliverable. Also, it is not 100% sure how much you need and why, as the conditions change, in particular as you get more intermittency and so forth. So it is very clear that you need software innovations to manage control centers in a more flexible way. How do you see that innovation? Because you have a couple of vendors who are actually managing these control centers is their software. And how do we make space for Lincoln Lab, people like to call this sidecar. You put a computer, you get state estimation data and show what different software would do and how it would help. How do you integrate innovative solutions to support more flexibility and therefore impact decarbonization? I don't see on the industry side much effort on that. Can you comment a little bit?
Yeah. First of all, my heart is with you. I started my career writing optimization, hydrothermodynamics, optimization of hydro and thermal plants for cooling, and more importantly, low frequency control and economic dispatch. And unfortunately, I spent a lot of time on unit commitment, which is not nearly as important in today's world. But having optimizing reserves is a real issue. On the polar vortex 2014, I was sweating bullets. We were down to 500 megawatt reserve on a 160,000 megawatt system. And it was primarily due to the same problem in Texas. The gas plants did not perform well at a minus 24 degrees. It was really the bottom line. So being able to optimize the reserves, and more importantly, being able to use load as a reserve, to be able to have more demand side management. At TVA, when I was there, we designed ESP, that's economy surplus power, is ESP in their case, has nothing to do with perception. But the bottom line is we increased the load side from 200 megawatts to 2,700 megawatts of load side interruptible. And I would add at PJM, we went from 2,000 megawatts of demand side up to something like 12,000 dependable interruptible. And when we tested it, it was air. We actually, it proved to have a better E4D, if you will, than the equivalent forced outage of a gas plant. So it was up in the 92, 93% available even on the hottest and coldest day. So computers that can take the distributed resources, aggregate them into reserves, and be able to call on them and be confident that they're there is a step in the right direction.
I can't resist my trick question that I don't know the answer to. What does it take longer, to build a new large transmission line or to do the next generation software and control center?
It takes longer to build a transmission line.
I am not sure.
And this is an interesting story here, 30 miles from me. TVA is building a $300 million state-of-the-art control center that has EMP shielding. It actually has ferrous particles in the concrete for EMP shielding. But getting a transmission line across adjacent land took longer than the design of an EMP control center. It does take, and I'll be brutally frank, most control centers now, it's not a wholesale change out of the system. At PJM, when we did the change out, it was a $213 million 4 or 5 year project that we had. Now it's components. Everything is modular. You replace the software, you replace some of the hardware. So it's in essence, how do I implement the next stage of the state-of-the-art technology in terms of software?
That is encouraging. I think Dan Wu has a question. Okay, so it's, I'll read the question. He said, I have a question regarding the DRs and inverter-based resources. Since they comprise many more components than traditional generation units, the probability of well-functioning for all the components will decline sharply. What can we do about it to prevent failure cascades?
It's called design standards.
Yes.
Unfortunately, we have let the inverters, and at PJM, we actually had a problem that people were dumbing down the inverters so they wouldn't have to do low frequency control or couldn't do low frequency control. And we passed a interconnection rule that said we had to have the ability to have a smart inverter with those equipment. He's absolutely right. The number of components and the fact that there's not a consistency of how they're designed is very troubling. And I had trouble here. I wanted a EMP shielded inverter for my home, and I only found one company, Solar, that knew what the heck I was talking about. But I said, I want 150 kV per square meter EMP shielding. So we need to work hard, and the ANSI standard process, the IEEE standard process, all of those are so slow that it really has got to be up to the government to some extent to step in and make sure that we have standards that will not allow us to build equipment that will cause electromagnetic interference between us and our neighbors' solar panels.
So we know, by the industry consortia and groups of people that are working on those avant-garde standards, newer standards, and I think it's extremely important. I see probably related question from Dr. Pallavi Bharadwaj, who is our postdoc at MIT. Pallavi, you want to ask your question?
Yes, thank you, Maria. So, hi, Terry. It was amazing
Hi.
to listen to you. Thanks to Maria, we are getting to listen to such amazing people in this seminar series like you. So, my question was, you really intrigued me when you talked about ADC microgrids, where you have AC and DC combined. So, I remember me and Maria and Dan, we were just discussing last week about AC versus DC microgrids, and we saw that DC has issues with protection, AC has issues with multiple stages of power conversion. So when you combine AC and DC power grids together, we were wondering how are you dealing with those challenges?
First of all, Arshad Mansour, the smartest guy in the room, no matter which room he and I are in, I wrote a paper about this 16 years ago, that if we could possibly have AC and DC microgrids, and he wasn't necessarily thinking about superimposed on the same existing wiring system, but the protection is not so tough if you're at the lower voltages. So if you're talking about HVDC, or you're talking about higher voltages of the DC, it's very hard. We do have a DC meter now that's approved, revenue quality DC meter. So the possibility of sales and transfers to be made is very, very important, because you got to get paid or you will not build out the DC. But the most important thing that I've seen with what's happening with ADC is the power quality on the AC system gets order of magnitude better. You don't have the kind of power quality issues that the existing harmonics of the DC inverters have across the entire system now. And we're actually, I don't know if we're getting smarter or better meters. And by the way, Elu, between meters and model, I'll always side with meters, the measurement. But we are measuring levels of harmonics that we've never seen before on the system. And part of that is the measurements are better. But a big part of it is the amount of asynchronous DC generation that's hooking into the grid. And it's an engineering problem. It will be solved. It has to be solved.
So it brings up the question of intercomponent, inter-area oscillations. Can you give us a little history on that?
Very little, because I'm not an expert. Out west, Bonneville has been by far the expert, and they created the PMUs because of inter-area oscillation. I grew up in the Eastern Interconnection, and we didn't know we had those until we improved the phasor measurement units and the ability that we had. As a matter of fact, Elu convinced me that we had equipment fighting with each other because we did not have the measurement systems in place until the FNet that she developed and the PMUs were put in place. Inter-area oscillations are going to get a whole lot worse before they get awful.
Yep.
And getting awful is not acceptable. I'm hoping that we can substitute the speed of the inverter, the speed of the electronics, I'll say it that way, for the beauty of the rotating mass and inertia we have on the system. But the eye opener I had was the Fly-Gammy fault that stayed on the system so long, is generators were fighting each other and everything was normal in between. So inter-area oscillations, and at the end of the day, the August 14, 2003 blackout, even though it took a long time to propagate, was caused by generators fighting each other and having inter-area oscillations.
So very long history on that problem. I remember early PhD students at MIT were doing with New York ISO with late Chuck King, if you remember Chuck King.
Yeah.
like when Oswego, when nuclear plant goes out, you have these 0.7 hertz oscillations. They didn't have to do anything with power electronics. They were literally, equipment fighting, as you said. And so it never was clear, and I don't think clear is to this day, and even late Prabha Kundu wrote about this, they exist. Are they don't blow up. They don't, they're just there on low frequency. Are they bad? Are they bad for the system or not?
Yes, because sometimes we can't dampen them. If you look at being, and I'll give you a wild and crazy example of something that happened to me. It was probably around 1995 or so. The power system stabilizers at Bath County started swinging against a nuclear plant in Alabama, 500 or 600 miles away. Everything else is pretty rock solid in between, but those two oscillations started happening, and we were moving 300 megawatts up and down. We took the voltage regulator out of service and the problem went away. So we said, we found it, it's the voltage regulator. We went through it engineering wise, there wasn't anything wrong. They had switched the power system stabilizers out of service at the same time, near the same time we switched the voltage regulator. So I think those problems are going to get worse as we go forward, and we've got to find the ways to dampen those. And I think batteries with power electronics that can respond microsecond, at least millisecond, can solve that problem.
So just to connect the dots, even with checking that early work that was done by Jeff Chapman and Eric Allen also, you can actually make, they were not autonomous, they were decentralized controllers, glorified PSS, power system stabilizers, they don't have to even exchange the information, that they'll cancel those inter-area oscillations. So there is a lot of university work that was done that actually never, patents expired. We had a patent with New York ISO on these, the patents expired. They were not adapted as next generation better controllers, for automation. This is one thing that I think is actually bothersome in power industry. There is too much analysis, too little emphasis on designing the autonomous controllers that work. And now we have power electronics. Well, you just put a lot of storage and you are done, but that's expensive. So who is going to be pushing next generation power electronics, inverters and stuff like that, that would actually be a stable business?
It has to be those that are buying the equipment. You have to write in your specs what you want. And to some extent, that requires the ISO RTO reliability coordinator, in the case of here in the Southeast, to put what's required of the equipment that you're going to interconnect. So the fact that we had people saying, hey, we don't want to be able to do low frequency control. And we actually went through a period in the 2010, 2012 period where even the gas turbines being connected to the system, the governors were being dampened so much that they wouldn't move. And people did not want to do low frequency control with those equipment. I'm a control freak. I believe in the large system control. I also know that you can measure the frequency and the harmonics and the swings that are happening locally, and you can respond locally without having the delay of having to communicate to a control computer and then back to the local. So there's no reason we can't have dampening occurred with the new power electronics. I will also add, if you're dealing with controls that are measured in microseconds instead of seconds, you better get it right the first time. You can't get in a position that you cause problems because of the controls.
I can't help but mention another sort of giant thinker like yourself in the industry, Dale Osborne, who used to say the same thing. He said, okay, if you want markets to do what they want to do, or you want to do scheduling of clean resources, you better know that those controllers, automation actually is not going to destabilize the system.
Yes.
And I think we are at that point. It's not just, so there is a very different challenge, even here at MIT, that when you evaluate the technology that like you need to build new transmission line, you just sort of still have on the economic side and the policy side, you still have just thinking in terms of capacity. So it's very hard to make the case on what is the value of things that you do better in operations in order to avoid these things that are really going to prevent you from utilizing more. So how do you connect? Is not NAE, you've been in NAE now for a while, are they recognizing that problem that it should not be capacity-based thinking anymore for policy? It's not just building the bigger thing and then you are done.
Yeah, the Grid of the Future report that went out in March of this year very much emphasized that DER is coming. It's coming in a big way, and that the system of the future has to have focus on the distribution network and the distributed energy resources and controls that are in place. And let me brag a little bit on the Electric Power Board of Chattanooga. I'm talking to you now on a mesh network that I installed just for this call. And I'm talking at something like 500 megabits a second on a 1 gig channel. As part of putting in the fiber optics to every home, they put in smart meters, they put in automatically sectionalizing, they reduce the outage time, and not necessarily the number of outages, but the outage time was cut probably by 2/3 by having all the automation in at the distribution level, and the fiber optic network allowed that automation to happen. And motor operated disconnects aren't fast enough to change everything, but it makes a huge difference in the duration of an outage if you've got automatic sexualizing with motor operated disconnects at the distribution.
So we maybe are pushing our, pressing our welcome with you, but I see Yilu still wanting to ask the question.
Oh, if Elu has a question, I'll call her back after the meeting and talk about it.
No, we can do it
She's
now.
one of,
Yilu, go ahead.
she's one of my heroes.
I know. Yilu, can you ask for everybody so we know?
Allow me, Maria. So it's really not a question. I have two. One is I know Terry going back and forth between Hawaii and Single Mountain. KIUC. I don't know, Terry. You visit the outer island near the home or not? But we have a project with KIUC, and they use. I heard you mention several times the storage and IBR connected fast acting. They actually use their energy storage to counter the frequency issues when they operate many times 100% renewable solar. So they're doing very amazing work.
Yeah, the island of Kauai got ahead of the rest of the world, and they did it before. They weren't waiting on just chemistry. They did it with lead acid batteries as we were working on improving the cost and performance of lithium. But I am blown away by the fact, first of all, they can't have wind on the Kauai Island, but they have had 100% renewables from time to time with the solar they put in, and it's a cooperative that the public actually owns the utility, and they've done a phenomenal job of saying how can we make 100% renewables work. But also they've had a couple of outages. And
I was just going to say that they just had one.
When you run out of energy storage, and you run out of fuel sometimes, whether it's like the gas plants of Texas on February the 15th, there is a value, and I'll show my bias here. I sure hate to see the nuclears that are shuttering shutter. Diablo Canyon, there was an article this week or last week saying, hey, these plants have 18 months of fuel on site. You can do a whole lot. Gas moves at 24 miles an hour, and just-in-time delivery and too dang late is about this distance apart when the gas is moving. So, in the case of Kauai, they've been on the leading edge, and they've significantly reduced the cost of electricity. At the same time, they have gone to a very high percentage of renewables. But that's a real good example of getting ahead. And we'll see Hawaii will continue to innovate in that the price of electricity based on Asian oil prices is such that you can do a whole lot more innovation if the price of electricity is 30 cents per kilowatt hour instead of 10 cents per kilowatt hour.
Well,
Yes. I'm glad you're intimately connected to that project. And right now, our work is basically help find a way to do inertial forecasting.
Yeah.
And they like to know how much inertia is the energy storage injecting. What is the equivalent artificial inertia? So that was a fun thing.
Yeah.
Have a quick.
Let me add just a point to that. We need university type people like you and Maria to be thinking about substituting speed for inertia. We know the inertia is there, it's automatic, you don't have to think about it, but we also know that with the speed of the inverters, we can have synthetic inertia, if you will, by having, you can't do that with probably wind or solar, but you definitely can do that with batteries where you got energy storage.
Yeah, that's true. Actually, you could, if you leave enough headroom, solar,
Yeah,
you would be able to, right? Yeah.
But a headroom of zero cost energy is going to be hard to come by.
That's right.
It's hard. It's hard. It would be hard for me to turn off the solar panels so I could have a spinning reserve here on Signal Mountain, especially.
But you can adjust your appliances a little bit.
Yeah.
Yeah.
Well, when our R&D staff at PJM would talk about adjusting refrigeration, I would say botulism if the control system fails, and you have. But there's a lot of energy mass. One of my favorite projects, by the way, Elu, was the Drexel University used their library for mass storage. After Google came into play, we knew the books were all in the library and what the mass of all that library books was, and we were able to pre-cool or preheat the library space and then transfer that heat and cool to other buildings on campus because of the huge mass of the building itself. Here,
well, that's amazing. I wonder if the books will sweat when they start to warm up, like everything else.
Yeah. You do have to do humidity control, but the room I'm sitting in has 8,000 pounds of granite, a trom wall of brick that stores energy from the sun. I did make one huge mistake. I hate it when I do that, but I do it from time to time. I wish I had put resistance heat under the 2¼ inch granite tile, because 3 days without sunshine, the floor gets dang cold out here.
That works. That makes sense. Yeah, maybe they should come up with retrofit. Have another follow-up with Maria.
Yes.
I bumped into this talk just by accident because I only received your first announcement when many months ago about this talk series, and I didn't receive any others. I'm pretty sure if you repeatedly announced on the Power Globe, this would have hundreds, several hundreds of listeners. So it would be good to post the talk, on the web and for people to access.
We will do that, and actually it will be, we will send, thank you, Ilo. I think we will send the information on where people can find the previous talks and then remind more people on Power Globe. It's well taken. Terry, I can't thank you enough. This has been absolutely amazing for me, you know, and I see for other people, and just, you know, huge thanks on behalf of everybody, and we'll stay in touch.
Send a bottle of champagne to Terry, because that's what that's what they do when you have a great talk.
Okay, great. Okay, I'll talk to you, Ilo, about some more pointers what to do exactly. I'll send you an email.
As I said, I quickly said yes when you asked, and it is an honor. I have tremendous respect for MIT and what you're doing in the entire industry and training the engineers of our future.
So we want to say, Terry, that I speak for young people. I see a lot of them whom I know here. It's good to get a little bit encouragement that we are doing something that matters. Sometimes it's hard, that's all. Yeah, thank you.